Alright, so these are the harmonic trigonometric identities which you may or may not be familiar with. But before you understand harmonic trigonometric identities, you need to understand what the function of trigonometry is. So, if we have sine and cos related in an equation and they are related such that they cannot be converted to a single function, nor can any trigonometric identity be used, such a function or equation is said to be the function of trigonometry. And this function of trigonometry can only be solved using trigonometric identities. Let's say, for example, we have this. We would send this to the right hand side and then cross multiply, or in other words, send 4 there and cos there, and we have tan, because we study the identity sin x over cos x is equals to tan x. Thus, this is not a function of trigonometry, since we could apply a trigonometric identity and convert this to a single function. And the rest of the part was solved as it. Moving on, let's say for example we have this. Instead of a 0, we have a 2 on the right hand side. This cannot be converted to a single function, and thus this is the function of trigonometry. In order to solve the function of trigonometry, we must apply harmonic trigonometric identities. These are the rules of harmonic trigonometric identities. We have two rules for sine and two rules for cos. In case of sine, plus goes with plus and minus goes with minus. Then for cos, instead plus goes with a minus, and for cos, minus goes with a plus. This is the difference between sine and cos. Whether we have to express it in this form or this form will be told to you by the question. If the question does not specify, you can use either method and solve the identity. Alright, so what is R and what is alpha? So alpha and R are constants calculated using these formulas. Alpha is always going to be acute, that is between 0 and 90, 0 and 90 non-inclusive, and R is the square root of a square plus b square. Alpha is tan inverse of b over a. So you need to be careful that how b and a can vary depending on what you have to express it. Let's say for example I am to express it in terms of sine. So I write sine first and cos first, and my a and b will be determined accordingly. Else if I were to express it in terms of cos, so I'll write cos first, then sine, then calculate the value of alpha according to my new b and a, and then write the minus or plus, which will be determined according to the sign in the middle. We'll take 4 examples to clarify our concepts. First of all, the example which we took but did not solve. So, in order to solve this, the first step is calculating the value of r. R is equals to square root of a plus b square. So, the question does not specify and we have sine first, so I'll express this in terms of sine. So something like r sine x minus alpha. Solving this further would give me 4 square plus 3 square, and r is equals to 5. Square root of 25, r is equals to 5. And moving on, I need to solve for alpha, or rather, just a second. Always try to do the working for r and alpha in one line. It makes it easier to understand, in my opinion. Saves up space too. So alpha is tan inverse of 3 over 4 b over a again. This would give me 36.87. Again, there is a background process to why we have these formulas, but you need not know them at this stage. And then we had to express it in this form. So r is 5 sine x. We had a minus here, and in case of sine, minus goes with minus, plus goes with plus, and we have a 36.87 is equals to 2, which was on the other side and remains as it was. We'll simplify this and solve this as a simple trigonometric equation. So we have 2 over 5. Now let's find alpha. So replacing this whole thing by alpha, I'll change the color. So alpha is equals to sine inverse of 2 over 5, and alpha is going to be 23.58. But before you should but before finding alpha, always remember to alter the range. I ignored it in this part, but you should never ignore it. I'll do it uh, I'll do it right now then. So this was the range given. I need to alter the range. I must alter the range, preferably as my first step in solving a trigonometric equation. So this is gonna be 360 minus 36.87 and minus 36.87. So this is my range. I'll make a graph for ASTC. ASTC lie in these quadrants, and since our expression is in terms of sine and sine is positive in the first and second quadrants only, so alpha is gonna lie there. Alright, and thus we can solve for x. So this is what we have. In the first quadrant it's 23.58. In the second quadrant it's 180 minus 23.58. So 23.58 in the first quadrant and 156.42 in the second quadrant. So when we move plus minus 36 there, it would become plus 36.87 obviously, and we can find the values for x. Rather, plus 36.87 plus 36.87. This would give me 60.45 and 193.29. We worked in decimals, In case of decimals, give your final answer to one decimal place, and this would be our answer. Or rather, I'm not sure about whether those values were rounded off to two decimal places or not, because this could be 5 or 4. I'm not sure. Thus, I leave them as it is for you guys to find out. Then moving on, example 2. First of all, let's find our a square plus b square. This is going to be 144 plus 25 and root of 169, which is 13. Then finding alpha, I have tan inverse over b over a, which is 5 over 12. This is going to be 22.6 degrees. I have a sign first and a plus here. Thus, it's going to be something like r sine x plus alpha, because in case of sine, plus goes with a plus. R is 13 sine x plus 22.6 degrees is equals to 4, which remain as it is. We'll simplify this, and this will become sine x plus 22.6 degrees 4 over 13. The first step is always adjusting the range, altering the range if needed. We need to do that, thus we'll do that. Just add 22.6 to everything, and this is what you'll get. So this is our new range. We'll solve for alpha. So alpha is sine inverse of, this whole thing was replaced with alpha, 4 over 13. And alpha turns out to be 17.9 degrees. So a graph of ASTC would look something like this. And sine is positive in the first and second quadrants. Thus, this is where our alpha would lie. 17.9, 17.9. All right. So we have a x plus 22.6 degrees. Just a second. This part is going to be very important. I repeat. I'm saying this the first time, but this part is very important. Because, see, 17.9 is not in the range, is less than 22.6. Thus, we not consider that. Instead, we add another 360 to 17.9, which is gonna give me 37, no, 377, 377.9, and this is in the range. You need to consider this, and this is a very important part. We'll solve for x, and we have 17.9, 37.9 minus 22.6 minus 22.6. This would give me x is equals to 139.5 degrees, 355.3 degrees. This is my third example. I'm considering all the possibilities which for rules of harmonic trigonometric identities which we learned here. We're done with these. We need to cover these. Alright, so moving on to example 3, let's speed things up a bit. So r is equals to square root of 2 square plus 3 square. This is 4 plus 9 square root, and this is square root of 13. Leave it as it is in exact form. This is the exact form, I repeat, not the decimal one. And tan inverse of b in this case over a. 56.3 degrees. The first thing you should have realized here is that we had a cos first, and thus we are converting this into a form like r cos. We have a plus here, thus x minus alpha. This is what we are converting it to. And if the question had asked us to convert it to sine, let's say, the only thing we do is we shift these things, but these values would change too, and thus it changes from question to question. For now, keep it as cos because we are considering all possibilities. So alter the range 0, x and 360. X is between 0 and 360 for now. We'll alter the range and this is what I turn out to have after subtracting 36.3 degrees from average. Just a second. Ah, it's 56.3 degrees. So we have r as 13, cos as it is, and alpha as minus 56.3 degrees is equals to 1 because we had a 1 there. It's always important to remember whatever was there and to write it down. We'll simplify this. So we have a cos x minus 56.3 1 over 13. Alpha turns out to be cos inverse of 1 over root 13, and alpha is 73.9 degrees. So this is ASTC. Cos was positive, and cos is positive in the first and last quadrants only. Thus, this is where alpha is gonna lie. We'll solve for x. So this is the range. Again, this whole thing is the range, and we must consider this. So x minus 56.3. I write this in yellow so I remember. And 73.9 degrees in the first quadrant, and 342.4 degrees in the last quadrant. Just wait a second. My bad. It's 286.1 degrees. Once I solve for x, this is gonna be x is equals to 130.2 degrees and 342.4 degrees. Then our last and final example, again in terms of cost, but we have a minus here, thus we need to express this preferably in the form of r cos x. There's a minus here, so there's going to be a plus here. Alpha, brackets closed. So this is what we'll work out for. and phi will remain as it is again. Remember this phi. So solving for r, the square root of 6 plus 8 square, ignore the sign for 8, and r turns out to be square root of 100, which is 10. Then solving for alpha, alpha is tan inverse of 8, ignore the sign again, over 6. This is 53.1 degrees. Always alter the range first too. So how about I shrink this and move this here, keep this here, and alter the range. So we have 53.10 degrees here. So altering the range would give me something like minus 56.1 degrees is less than equal to theta plus 50 theta. Wait a second. It's, yeah. So 56.1 degrees is less than equals to theta plus 56.1 degrees is less than equals to 413.1 degrees. So once we have the range, we'll simply express this in terms of, we'll express this whole thing like this and then solve for alpha, or rather for x. So r is 10, cos remains as it is, x plus 53.1 degrees is equals to phi. Where did the phi come from? We had a phi here. Simplifying this would give me cos x plus 53.10 degrees. So I have a phi over 10 and half. Thus I have a half here because 1 and then then solve for alpha first and then for x. And alpha turns out to be 60. So cos is positive in the first and the last quadrant. So this is what ASTC would look like. And alpha plus 53.1 degrees is equals to 60 degrees and 300 degrees, which perfectly fall in the range. So solving for theta would give me something like this. Just a second. And this is our final answer. These are either our two final answers which fall in the range. So we are done with 4 examples and all types of harmonic trigonometric identities which could be applied.